What if the most terrifying monsters in the universe were not creatures, but invisible giants waiting in the dark? Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They bend time, swallow stars, and challenge everything we know about physics. Tonight, we journey into the heart of these cosmic mysteries to uncover what happens when the universe itself collapses into a single point. Black holes are often described as cosmic monsters. They lurk silently in the universe, unseen, waiting for anything unfortunate enough to cross their path. But unlike the monsters of myths and horror stories, black holes are not creatures born of imagination. They are the inevitable outcome of nature's most violent processes. To understand them, we must begin with something deceptively simple: a star. Every star you see in the night sky is locked in a delicate battle. On one side, gravity pulls inward, trying to collapse the star into itself. On the other side, nuclear fusion in the star's core pushes outward, generating immense heat and light. For millions, even billions of years, this balance keeps a star alive. But stars, like living things, are mortal. And when a star with enough mass reaches the end of its life, the battle between gravity and fusion ends in catastrophe. When a massive star runs out of nuclear fuel, its core can no longer support the crushing weight of its outer layers. In an instant, gravity wins. The core collapses, crushing atoms together with unimaginable force. Electrons and protons are squeezed into neutrons, and the collapse accelerates. The outer layers of the star explode outward in a blinding supernova, one of the most violent events in the universe. What remains behind is something extraordinary. If the star was large enough, its core collapses beyond the neutron stage, past the point where matter as we know it can exist. Space itself caves in, and a black hole is born. A black hole is not a physical object in the traditional sense. It is a region of space-time where gravity has become so intense that escape is impossible. To cross its boundary, known as the event horizon, is to pass a point of no return. Beyond that invisible line, not even light, the fastest thing in existence, can find its way back out. But how can something that cannot be seen be studied? This is one of the most thrilling aspects of astronomy. Scientists cannot simply look at a black hole, because by definition, it emits no light. Instead, they study the chaos around it. When gas, dust, or even entire stars are pulled toward a black hole, they spiral in at tremendous speeds, forming what is called an accretion disk. Friction and compression heat this disk to millions of degrees, making it glow brightly in X-rays. To telescopes, these X-ray signals are like the footprints of a monster, indirect evidence of something too powerful to reveal itself directly. The scale of these cosmic beasts defies comprehension. A black hole formed from a single massive star may contain several times the mass of our sun, compressed into a sphere barely 20 miles across. Imagine the sun, which could fit more than 1 million Earths inside it, crushed into an object the size of a city. That is the power of gravity unleashed. And then there are the supermassive black holes. These are not born from a single star's death, but instead lie at the hearts of galaxies, including our own Milky Way. They contain millions, even billions of solar masses. Some are so large that if you placed one at the center of our solar system, its event horizon would swallow every planet all the way out to Jupiter. These titans control the very architecture of galaxies, influencing how stars form and where they cluster. Yet, despite their size and power, black holes are not vacuum cleaners that indiscriminately suck everything around them. If our sun were replaced by a black hole of the same mass, Earth would continue orbiting it in exactly the same way. It would simply be dark and cold. Gravity works the same way outside the event horizon as it does for any other massive object. It is only when you cross that invisible threshold that the rules of reality break down. This is where the black hole becomes not just a physical object, but a gateway to the limits of human knowledge. Inside the event horizon, our understanding of physics collapses. General relativity predicts that everything falls toward a singularity, a point of infinite density and zero volume. But quantum mechanics tells us that nature does not allow infinities. Somewhere, hidden in the fabric of space-time, lies a deeper truth that unites these conflicting ideas. That truth remains one of the greatest mysteries of science. Astronomers continue to push technology to its limits, to peer closer and closer at these enigmatic giants. In 2019, humanity glimpsed the unseeable when the Event Horizon Telescope captured the first ever image of a black hole's shadow in the galaxy. May 87? It was a fiery ring of light surrounding a dark abyss, a picture that shook the world and confirmed decades of theory. For the first time, we were staring directly at the edge of the unknown. Black holes force us to confront questions that are not just scientific, but philosophical. What happens to matter and information that falls inside? Does it disappear forever, or is it somehow preserved? Could black holes be portals to other universes? Or tunnels through space-time itself? These are not questions for science fiction alone. They are questions at the cutting edge of modern physics, being explored right now in laboratories, observatories, and by some of the brightest minds alive. From the death of stars to the birth of cosmic monsters, black holes represent the extremes of nature. They are terrifying and beautiful, destructive and creative. They mark the boundaries of our understanding and hint at wonders we have yet to uncover. And while we may never escape their grip, by studying them, we may finally unlock the deepest secrets of the universe itself. Approaching a black hole is like stepping into a realm where the rules of reality no longer behave as we know them. The closer you get, the more the universe itself seems to unravel. Distances warp, light bends, and even time, our most constant companion, begins to lose its meaning. To venture toward a black hole is to witness the fabric of space-time stretch to its breaking point. Imagine you are an astronaut, daring enough to travel near one of these cosmic abysses. As your spacecraft approaches the event horizon, strange things begin to happen. From your perspective, everything seems normal. You continue to tick seconds on your watch, your heartbeat stays steady, and your ship drifts closer. But to an outside observer, watching from a safe distance, something extraordinary occurs. You appear to slow down. This is time dilation, a consequence of Einstein's theory of general relativity. Gravity is not simply a force pulling objects together, it is the bending of space-time itself. The stronger the gravity, the more space-time warps, and the more time itself is stretched. Near a black hole, gravity is so extreme that time passes at dramatically different rates depending on where you stand. For the astronaut falling inward, minutes feel like minutes. But for the distant observer, those same minutes could stretch into hours, years, or even centuries. As you hover on the edge of the event horizon, you would seem to freeze in time, suspended forever in the last moment before crossing the threshold. Light escaping from your ship would grow weaker, stretched into longer and longer wavelengths, fading from visible light to infrared to microwaves, and finally disappearing entirely. To the outside world, you would vanish not with a scream, but with a slow, silent fade. And what of the astronaut's perspective? Passing the event horizon is not a sudden, violent moment. There is no wall of fire or crash of energy. You would drift across without even noticing. But the universe outside would slip away from you. Once across, no signal, no beam of light, not even the fastest message in existence could ever escape to tell your story. The cosmos would be cut off from you forever. The most terrifying fate, however, lies in what scientists call spaghettification. Gravity near a black hole does not act evenly. The side of your body closer to the black hole is pulled with slightly more force than the side farther away. Normally, these differences are microscopic, but near a black hole, the difference becomes catastrophic. Your body would be stretched vertically and compressed horizontally, like pasta pulled by invisible hands. Molecule by molecule, atom by atom, you would be torn apart. This gruesome process is not science fiction, it is a direct prediction of the laws of physics. Even light itself is not spared. Black holes bend the very paths, photons travel, distorting the view of the universe behind them. This effect, known as gravitational lensing, creates surreal illusions. Stars duplicated, galaxies smeared into arcs, entire regions of space mirrored around the black hole's edge. To look at one is to peer into a cosmic funhouse mirror one, crafted not by glass, but by gravity itself. Perhaps the most haunting idea is this: once inside, time and space may trade roles. The singularity at the heart of the black hole is not simply a place, it is a moment in time you are destined to reach. No matter how you maneuver, no matter what engines you fire, every possible path leads inexorably to that final point. Just as you cannot resist moving forward in time, you cannot resist falling toward the singularity. It is as though the universe itself commands your fate. Yet, not all black holes are equal in their horrors. For smaller black holes, the tidal forces that cause spaghettification would tear you apart long before you reach the event horizon. But for supermassive black holes, the titans at the centers of galaxies, the event horizon is so vast that you could cross it intact. Only deep inside, closer to the singularity, would those destructive forces finally overwhelm you. This means, at least in theory, you could survive the crossing for a time, drifting inside a one-way prison from which no escape is possible. And here lies one of the greatest paradoxes in science. What truly happens to matter, to information, once it is consumed by a black hole? Physics tells us that information should never be destroyed, but black holes seem to erase it from the universe entirely. This clash between the certainty of quantum mechanics and the predictions of general relativity has led to one of the most heated debates in modern science, the black hole information paradox. Some scientists propose that information is somehow encoded in the event horizon itself, like a cosmic hologram. Others suggest that what we call a black hole might actually be more complex, with layers of hidden structure we have yet to imagine. And still others dream of more exotic answers: wormholes leading to distant parts of the universe, or even gateways to entirely new realities. For now, the truth remains out of reach, locked behind an invisible wall where even light cannot return. But with every observation, every theory, and every daring experiment, we take one step closer to uncovering what lies beyond the abyss. Black holes are not just monsters, they are messengers, pointing us toward a deeper understanding of space, time, and the ultimate nature of reality itself. If stellar black holes are monsters, then supermassive black holes are gods. They sit at the centers of galaxies, invisible yet commanding the fate of billions of stars. These titans are so immense that words struggle to capture their scale. While a stellar black hole may weigh 10 times as much as our sun, a supermassive black hole can contain millions or even billions of solar masses, compressed into a region smaller than our solar system. Take, for example, the one at the heart of our own Milky Way. It is called Sagittarius A star. Buried 26,000 light years away, this invisible giant holds about 4 million times the mass of our Sunday, and yet, from Earth, we cannot see it directly. For decades, scientists only suspected its existence because of the way nearby stars moved. They weren't drifting randomly, but whipping around an unseen point with staggering speed, as if tethered by an invisible anchor. Only something with the gravity of a supermassive black hole could explain their motion. But Sagittarius A star is modest compared to others. At the center of the galaxy M87 lurks a monster so large it defies comprehension. 6.5 billion solar masses compressed into a region smaller than our solar system. In 2019, the world was stunned when astronomers used the Event Horizon Telescope to capture the first ever image of its shadow. What they revealed was a glowing orange halo surrounding a dark void, a cosmic ring of fire encircling the unseeable. It was proof not just of black holes, but of the human ability to reach across light years and photograph the impossible. Supermassive black holes are not passive giants. They shape the very galaxies that host them. As matter spirals into their depths, it heats to incredible temperatures, blasting out energy in powerful jets that can stretch for thousands of light years. These jets, invisible to the naked eye but blazing in radio and X-ray wavelengths, can regulate the birth of stars, quench galactic growth, and even sculpt the structure of the universe on the largest scales. Without supermassive black holes, galaxies as we know them might not exist at all. This raises a haunting question. Which came first, the galaxy or the black hole? For years, astronomers assumed that galaxies formed first and black holes grew within them. But mounting evidence suggests a far stranger possibility that black holes may have formed in the early universe, even before galaxies, and then acted as seeds around which galaxies assembled. If this is true, then black holes were not born as cosmic afterthoughts. They were architects, laying the foundations of the cosmic cities of stars we see today. The influence of these giants extends across billions of light years. Quasars, some of the brightest objects in the universe, are powered by supermassive black holes, devouring matter at furious rates. These cosmic beacons can outshine entire galaxies, blazing so brightly that we can see them from the farthest reaches of the universe. To witness a quasar is to look back in time to the era when the first galaxies were forming and black holes were already shaping the young cosmos. Yet, despite their enormity, supermassive black holes remain cloaked in mystery. How do they grow so large? Some theories suggest they build mass over billions of years, feeding slowly on stars and gas. Others argue that in the early universe, conditions were so extreme that massive black holes formed directly, bypassing the usual stellar collapse. The truth may be stranger still, hidden in the first few 100 million years after the Big Bang, a time we are only beginning to glimpse with new telescopes like the James Webb Space Telescope. For us, these giants are not just distant curiosities. The fate of our own galaxy is tied to its central black hole. In about 4 billion years, the Milky Way will collide with its neighboring galaxy, Andromeda. At the heart of each lies a supermassive black hole, and when the galaxies merge, so too will their titans. The collision will unleash gravitational waves, ripples in space-time that will echo across the universe. For civilizations that might exist in distant corners of the cosmos, those waves will be a faint but undeniable signal. Two galactic hearts becoming one. Supermassive black holes remind us that the universe is not a quiet, empty void, but a dynamic and violent place where creation and destruction are intertwined. They are the engines of galaxies, the sculptors of stars, and perhaps even the architects of the cosmic web itself. To study them is not just to study gravity, but to confront the forces that shaped everything we see when we look up at the night sky. They are, in a sense, the pulse of the universe. Silent, hidden, yet unimaginably powerful. And as long as galaxies exist, their hearts will beat with the rhythm of these invisible giants. For most of human history, black holes were only an idea, mathematical curiosities scribbled in the margins of Einstein's equations. Astronomers could not see them, touch them, or confirm them. They were whispers in the mathematics of relativity, haunting the background of science, like shadows we weren't sure were real. But in the last few decades, that shadow has come into the light. Black holes are no longer just theory. They are observed, measured, and in some cases, even photographed. One of the greatest breakthroughs came in 2015 when the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, captured something humanity had never witnessed before: the faint ripples of space-time itself. Two black holes, each dozens of times more massive than the Sun, had collided more than 1 billion light-years away. Their merger unleashed a storm of energy so violent it shook the very fabric of the universe, sending gravitational waves racing outward at the speed of light. By the time they reached Earth, the ripples were smaller than a fraction of a proton, but our instruments were sensitive enough to hear them. It was as if the universe itself had spoken, confirming a prediction Einstein had made a century earlier. Since then, LIGO and its European counterpart Virgo have detected dozens of these cosmic collisions. Each one is a message from the deep, proof that black holes are not silent tombs, but dynamic actors in the ongoing story of the cosmos. Some of the black holes detected are far larger than scientists ever expected, forcing us to rethink how these giants form. With each detection, the universe grows stranger and more alive than we had ever dared imagine. Then came 2019. For the first time in history, humanity captured an image of the unseeable. Using a planet-sized network of telescopes called the Event Horizon Telescope, astronomers revealed the first photograph of a black hole's shadow nestled in the galaxy Mate 7. The image, a fiery ring surrounding a bottomless darkness, was more than just a picture. It was a milestone in human curiosity. For centuries, black holes had been invisible phantoms. Now, we could point and say, there it is. The success of the Event Horizon Telescope did not end there. In 2022, the collaboration revealed a second image, this time, of Sagittarius A star, the supermassive black hole at the center of our own galaxy. Unlike the monster in May 7, Sagittarius A star is far smaller, and its turbulent activity makes it harder to capture. But after years of painstaking work, the image emerged. Another glowing halo. Another glimpse into the abyss that governs our galaxy's core. And yet, the images raise as many questions as they answer. How exactly do these monsters feed? Why do some black holes launch jets of matter that stretch across thousands of light years, while others remain eerily quiet? What role do magnetic fields play in shaping their fury? To push deeper, scientists turned to another instrument, the James Webb Space Telescope. With its unprecedented sensitivity to infrared light, Webb peers back billions of years to the dawn of the first galaxies. And what it has found is astonishing. Even in the early universe, barely a few 100 million years after the Big Bang, black holes appear already fully grown, some with millions or billions of solar masses. How could they have grown so fast? What engine could possibly feed them quickly enough in such a young cosmos? This puzzle has forced astronomers to reconsider the story of cosmic evolution. Perhaps black holes form directly from colossal clouds of gas collapsing under their own weight, bypassing the usual stellar deaths. Or perhaps exotic physics forces and particles we have yet to discover accelerated their growth in ways we cannot yet explain. Every new observation pushes the frontier of our ignorance further, reminding us that the universe is always stranger than we think. Even the nature of the black hole itself remains uncertain. The information paradox still looms, pitting the smooth geometry of Einstein's relativity against the unpredictable quantum world. If information truly cannot be destroyed, then the black hole must hide some deeper truth, one that could revolutionize physics itself. Is the event horizon a thin, holographic shell encoding all that falls inside? Or is reality more radical, stiller black holes, gateways to other regions of space-time, perhaps even to other universes? For now, these remain questions without answers. But they are not hopeless mysteries. They are challenges, waiting for the next generation of explorers. With each improvement in technology, with every new telescope and detector, we peel back another layer of the cosmic veil. Black holes have gone from whispers in mathematics to roaring voices in our instruments. We can hear them collide. We can see their shadows. We can trace their influence across billions of light years. And yet, we are still only at the beginning. Each discovery sharpens the edge of the unknown, drawing us closer to the heart of the abyss. One thing is certain, black holes are not just the end of matter, they're the beginning of questions that might lead us to the ultimate laws of the universe. Until now, black holes have been distant curiosities, monsters observed through telescopes, studied with equations, and feared for their destructive power. But what if, in the far future, humanity could not only understand them, but use them? What if black holes, the very objects that defy comprehension, became the engines of our survival among the stars? It sounds like science fiction. Yet, some of the greatest physicists have dared to imagine this possibility. Black holes are, in a sense, the most efficient power plants in the universe. When matter falls into a black hole, it does not vanish quietly. Before it crosses the event horizon, it spirals inward, colliding, compressing, and heating to unimaginable temperatures. In this furious dance, matter can convert up to 40% of its mass into energy, a staggering efficiency compared to the mere 0.7% produced by nuclear fusion in stars. If humanity could somehow capture this energy, a single black hole could power civilizations for eons. This idea is known as the Penrose process, named after physicist Roger Penrose. He theorized that if we could drop matter into the outer region of a rotating black hole, the so-called ergosphere, we could extract energy from its spin. In principle, this could give us a source of power far beyond anything we could ever achieve on Earth. A civilization harnessing black holes might live not just for millennia, but for billions of years, drawing on the most fundamental wellspring of the cosmos. Then there is the concept of Hawking radiation. In the 1970s, physicist Stephen Hawking made a shocking prediction. Black holes are not eternal. Due to quantum effects near the event horizon, they slowly leak energy in the form of faint radiation. Over unimaginable spans of time, black holes evaporate and vanish. But in theory, advanced civilizations could accelerate this process, manipulating Hawking radiation to release bursts of energy. Some scientists even speculate that tiny, artificial black holes could one day serve as controlled power sources, compact stars of darkness engineered by intelligence itself. Of course, the dangers are equally staggering. Approaching a black hole would require technologies far beyond our current understanding. Propulsion systems capable of traversing light years, shielding against deadly radiation, and precision control in the most hostile environment imaginable. A single miscalculation and the same gravitational forces we seek to harness would tear a ship apart in an instant. Yet the dream persists. Black holes may also serve purposes beyond energy. Some theories suggest they could be used as gateways, wormholes linking distant parts of the universe. If this were true, a civilization could cross the galaxy in the blink of an eye, not by traveling faster than light, but by stepping through the shortcuts carved by space-time itself. Whether such wormholes are stable or even real remains uncertain, but the mathematics does not forbid them. And where math permits, human imagination will follow. Even if wormholes remain forever fantasy, black holes might still serve as tools of exploration. By observing how they bend light and warp time, future scientists could test the deepest laws of physics. They might probe the quantum structure of space-time or uncover the theory that unites gravity with the subatomic world. In this sense, black holes are not barriers, but keys, portals to knowledge as much as to destruction. What role, then, could black holes play in humanity's future? Perhaps they are stepping stones to becoming a true spacefaring civilization. Perhaps in a distant age, when the stars themselves have burned out, civilizations will huddle around black holes, drawing on their energy as the last flickering lights of the cosmos fade away. In that far future, black holes may not be monsters at all, but lifeboats, sanctuaries in a dying universe. The idea is haunting, almost poetic. The same objects that mark the death of stars could one day ensure the survival of intelligence itself. They are both tombs and cradles, destroyers and creators, depending only on how we approach them. For now, these possibilities lie far beyond our grasp. But history has shown that what begins as myth or imagination often becomes science. Once, the idea of flying to the moon was madness. Once, the thought of peering to the edge of the universe was unthinkable. Today, both are real. Tomorrow, who can say what doors black holes may open? The truth is this: black holes are not merely ends, they are beginnings of knowledge, of power, perhaps even of destiny. And as long as we look to the stars, we will dream of taming the darkness. Black holes remind us that the universe is not just vast, it is mysterious, dangerous, and beautiful all at once. They are the places where our science reaches its limits, where time and space collapse, and where the deepest secrets of reality still hide. But this is only the beginning. Out there, beyond our skies, lie countless wonders waiting to be uncovered, phenomena stranger than fiction, truths brighter and darker than we can yet imagine. If you've enjoyed this journey into the abyss, make sure to subscribe to Dual Suns. Together, we will continue to explore the darkest and brightest secrets of the cosmos.